you're right that there's a much bigger epistemic worry in terms of the fact that we don't yet have a quantum gravity theory. So in classical general relativity, when we try to extrapolate backwards through time, we come to this place where the temperature is unboundedly high, the pressure is unboundedly high, the density is unboundedly high. In classical singular models of the Big Bang, when you approach that point that we call the singularity, all these different quantities, like the pressure, the temperature, the space-time curvature, and so on and so forth, those all race off to infinity. And so we end up in a situation where we have very good reason to think that we're outside the domain of any of our currently known physical theories. In other cases where you might find, there might be something outside of the domain of our physical theories, you might have imagined constructing some kind of experiment. One example, there's something called a quark-gluon plasma. So when we make these extrapolations backwards using known physical theories, we come into a context where nuclei are no longer stable, and it just forms this big cloud of quarks and gluons all swarming around. That we can actually test independently. So we can go to there are laboratories where people produce quark gluon plasmas. But when you're doing this extrapolation backwards, you come to a regime where you couldn't have any kind of experiment to do any kind of independent test. And in that context, the only kind of test that you could possibly have is the data that you get from the early universe. Right? So you have this context where you can't independently check the extrapolation you're making. And then you might become quite worried about whether or not the kind of physics we might put there is correct, given that there's no independent way to check.